So that's how we selected the glazing. So the atrium, as I said before, went with the spectrally selected glass. The level 8 windows, since we're putting in new windows anyways, it was a small cost upgrade to put in low E glazing over the double glazing we were putting anyways. Heat recovered ventilation. So this building puts 31 cubic meters a second of air into it. It's a big building. So that's a large amount of air. We'll talk about that in a minute for indoor environment control. But that 31 cubic meters a second of air goes in through a heat recovered ventilation system. So outgoing air goes through a heat recovery wheel and preheats the incoming air. So if you look at if you ignore for a moment the fan energy cost of doing that, if you look just the amount of heat you're recovering over a whole year for that building, you're recovering 22 kilowatts per square meter. What the hell's that mean? I don't even know what that means. I did the model, right? So to make it useful to you to know that, is that the rest of the boilers in the energy room says it uses 30. So we're recovering almost as much heat through those big boxes on the roof in the plant room as we're spending on the boilers over the whole year. That's a huge amount of energy. When you think about a building, you're trying to design a low energy building, there's essentially two ways to think about energy flow through the building. Think about flow through the skin, which is either radiation or conduction. Right? And then there's the intentional exchange of air. You don't want to breathe inside the building, you want nice fresh air. So you want to recover as much energy as you can from that air you're exchanging and dumping out the windows, so you don't have to pay for it. So this building, because it's got heat recovered ventilation, recovers quite a bit of energy, almost as much as it's putting into boilers, just from the incoming air. Which is why a lot of times there's just one boiler running, and sometimes that's not even needed. Because the people inside, creating all the heat inside the building, all that exhaust heat is preheating the incoming air. We've got intelligent lighting control throughout the building, occupancy sensors, dimming. It's all linked to the BMS. I'll get that in a minute. Okay, so that saves power. Building tuning. During the tuning process, we noticed the optimum start routine wasn't working properly, so we were able to tune that up and fix that. The air flows were tuned to, we had sections of the building that were stuffy than others, so even though we commissioned the building properly, our commission, during the tuning process we were able to go back and fix that because we noticed those problems and could sort them out. And cooling as well, so all those points were tuned. The biggest one I noticed, I was surprised with, was just how wonky the optimum start was in this case, and how an easy to fix it was because we had the tuning team on board and able to just go ahead and do that as part of the process. It didn't take a call, hey, why is the boiler running when it's not supposed to be, from building management. It was already taken up by the team. Also, the building tuning team, intentionally or not, ended up being the punch list chasers, which is always in a big project. You've always got your punch list before you leave the building. Well, the tuning team was able to chase that punch list down. Okay, so the final two big bullets at the bottom. So I don't like to compare models in the end. Like when you've got measured data at the end, I don't like to compare it to models because all models are wrong, just some are useful. So what matters in the end is how much money you pay and how much money you would have paid for something else. So in this case, we've got the measured water use, I put reduced by 64%. So a typical commercial office building in New Zealand uses about 1,000 liters per square meter of office space. So Grants did a bunch of research, and somebody at Victoria University did that. No. So this building uses around 360 instead of 1,000, so that's 36%. So you're saving 64%. Now, just to make that sound a little better even, we have showers, and showers are used a lot in this building. 10% of our water use is going to showers, which for an office building is huge. There was some people on the design team that said perhaps we don't need quite that many showers, but they are used quite a bit. And then finally, again, sort of the same number. So the measured energy use, I said reduced by 46%. So we're using roughly half the energy of a similar size commercial office building. So that's enough to power about 170 homes, average use. So it's a relatively large impact for energy savings on that building. So you think 170 houses can power themselves, what you're saving in energy that you're not paying for that building. All right, next. Sweet. All right, so the next thing, so we just talked about things that kind of keep money in your pocket, and next we'll talk about things that make the building worth it. Indoor environmental quality. When you walk into a building, you're looking to lease an office space. How this space feels, how it looks, is really important. As an engineer, I don't like to use the word looks too much because I'm an engineer, right? But anyways, I mean, how the building space is, if I feel it's stuffy, if I don't like the space, I'm not willing to pay as much for it. So this is important. So the building is designed for excellent air quality. We use low VOC emitting materials in the paint, in the timber, in the carpet, in adhesives, sealants, all that stuff, ceiling tiles. So all that stuff adds up to less crap in the air that you got to deal with when you move into the building. When they lay down carpet, I don't know if you've ever been down when they put carpet in with standard cheap adhesive, it reeks. Low VOC carpet adhesive. The tenant areas have dedicated utility risers, so over the photocopy areas they can connect into their own dedicated tenant exhaust riser. So the exhaust over the copier, which is next door, goes up that exhaust riser and goes out to the heat exchange, in this case the heat recovery system, and goes out to space, out to the rest of the planet. But it doesn't stink next to the copier room because they've got their own duct system to pull the air out. The outside air rates in the building for the New Zealand Green Building Council's loading in the building, we've got 2.5 times code. Fresh air in the building. The building's fresh, not stuffy. And we've got a CO2 monitoring and control system. So we monitor CO2 levels throughout the building. It's easy in the building control system to go in and tune that, pick which CO2 levels you want in the building, and it reduces ventilation rates. So if you've got low occupancy over the weekend, the ventilation system's running, it drops down the air rates to keep the CO2 levels reasonable. And again, if you have a lot of people in the weekend, it brings the ventilation rates back up again. The building's designed for visual comfort. In that, I mean illumination levels. So not necessarily how beautiful it is. The lighting system is designed to provide good illumination levels of desktops. There's external views of the harbor. All that adds up to your point for the Green Star credit. And the lights are intelligent and auto dimming. So as the sunlight comes up, the lights dim slowly. And as the clouds move across and it gets dark out, the light levels come back up again. One good example is we had an area of the building where we had a contrast problem. So there's a lot of sunlight coming in from the atrium. And because of that, even though the light was tuned and commissioned properly at the right levels, it seemed kind of gloomy in that half of the building. So it was quite simple for Greg Blackwell in this case to go in and bring the light levels in that part up. Just change a few settings in the computer, bring the light levels up in that area of the building alone, and reduce the contrast, so everybody's happy with the light level in that building now. We didn't bring the whole light levels up in the whole bloody building, just that one area. All right. Lessons learned. There's a lot of lessons learned in this project, but I tried to keep just a few of the ones. First one was Wellington's not equal to Auckland. You know, when you start a project, you try to bring in all the best resources you can. And there's certain Green Star credits that are easier to achieve in Wellington, certainly CBD, than it is perhaps out in the outskirts of Auckland, for example, transport credits. But there are also credits that are not easy to achieve in Wellington that would be easy in Auckland. Concrete was one of those. I didn't write it down. But at one point, we were actually considering in our least respectful moments, that's not the right word. I don't know, anyways, we were actually, honestly, for a few minutes, we actually considered importing aggregate from the center of the North Island down here to get the recycling credit. It was a really dumb idea. We got pulled up short on that pretty quick, but we did think about it for a little while. In Auckland, it's quite easy to specify I'll call it eco-concrete, a low embodied energy concrete, a lower embodied energy concrete. That's Environmental Choice New Zealand rating. So you can get that concrete materials credit quite easily, and been told quite inexpensively as well in Auckland. But you can't do that in Wellington because it's not available here. And you obviously can't import mixed concrete from Auckland. Green Star is flexible, which is both good and bad, right? So a good example is we wanted visitor bike racks out front. We'd like to target that because it's an easy point, it's inexpensive, and it's nice to have. But we had this heritage requirement. We couldn't have a covered structure. Okay, well, we're meeting we're meeting the aim of the credit, which is to have visitor bike parking, and it's a wind sheltered area. So we were able to go ahead and put in CIR paperwork to get everybody to agree that that would work. On the bad side, it means that some of the credits you're not really sure at some point whether or not you're gonna hit them or not, because it's so flexible. It's like, where in the space are you? So there's a bit of work around that. So a lot of phone calls. Lesson learned: suppliers are getting better. Steel and PVC turned out to be much, much easier than we thought to hit. PVC turned out to be a matter of educating our QS and a few suppliers is what it came down to. So we achieved all the PVC credits in this building. It also helped that the PVC credit changed during the process of this building, so we were able to use the new credit. Paperwork wasn't as integrated as it could have been. At the end, Helen, who's around here somewhere, what's here, oh, there you are, I see you in the back, had to do a bit of chasing so that the subcontractors had done, for example, the painting contractor had done used the proper paints in the proper areas, but we didn't, she had to do a bit of chasing to get all the paperwork sorted. And last thing, so during the design process, and later during the build process, we talked about neighbors NZ, whether or not we should include the metering for that. And each time we said, well, it's not required. Who's going to pay for it? Nobody wanted to pay for it, so we didn't do it. Now, the person who did the wiring for the building wired it so it was all set to get the meters plugged in anyways, so it turned out to not cost anything extra. But it turns out, so now this building has been retrofitted for neighbors NZ metering, but they will, they don't have that first 8 months of data, so they're going to have to start their 1 year, a couple months ago now. Was it 2 months ago? Yeah, July, okay, 2 or 3 months ago. So they went ahead and retrofitted that metering in, which was relatively simple, but it would have been nice to have done it from the start. So from now on, I'll lean harder on that part. All right, questions?